So at Google, I feel like, you know, we're a bunch of software engineers and sales and so on, and many of us engineers are frustrated physicists. You know, we would have loved to be experimental and theoretical physicists as we grew up, but you know, we had to settle for Google. So we all take a pretty strong interest in things going on, especially with the Large Hadron Collider. I think you've probably all seen the doodle we did a couple of years ago when everybody was concerned that you would create a black hole that we would all get sucked into. So we have a bit of fun with it as well. And we've also done Street View inside the LHC. So people can get a sense of what it's like to be inside the LHC by kind of walking around it virtually. Do we have any, from the Google side, do we have any physics undergrads in the group? Oh, only one. Okay, fine. You're definitely on for asking a question. But many of us are fascinated by what's been going on and have been incredibly excited to live through vicariously this sort of historic event that's happened in the last couple of years. But with that, I'd like to turn things over to Mark Levinson, who is the director of this movie, to introduce the other panelists.
So just I'll give a little bit of a introduction of what's going on here. I don't know how many people know about this film. We've been working on it for years. David Kaplan first had an idea to do something like this. He is a theorist and saw that something was happening that was going to be monumental and was a unique situation in the history of science where something was going to turn on. I mean, you want to just give a little intro, Dave, before Savas gets back?
Sure. Hello. Yeah, about in 2006, I did a calculation that any theorist could do and discovered that somebody needed to make a documentary film. And I was the only one in my field willing to do something like that. And so I bought a camera, started doing interviews and discovered I didn't know how to operate a camera. And then had to figure out how this film was going to be made. I didn't really have a desire to make a movie. I had a desire for this movie to be made. But I understood that it had to be made from somebody who was deep inside the world and sort of living it. Somebody who was not going to be intimidated by the physics, but understood that this was a human drama and that this was a side of science that I never see captured in any other way. So I wanted to see it, and I wanted to feel it, and I wanted my friends to be known because these are my favorite people in the universe, and I didn't understand why everybody didn't know about them, and I didn't understand why this amazing event was going to happen and nobody's going to know about it. I ended up being wrong about that. It was all over the papers, but that was the original motivation. And then Mark discovered some crazy physicist wanted to make a movie, and Mark's training is a PhD in particle theory, and then went on to make movies, which is the natural progression. And then, he's the only one in that Hollywood gang who would really understand immediately that there was an incredible story there, that the humans that are doing it are amazing and interesting, and that you can create something dramatic out of something that sounds incredibly technical.
And here we are, many years later, with an incredible cast. And so actually I'm going to roll as just an introduction. We have the trailer that we have released. And so why don't we roll the theatrical trailer? Clip 1.
Thank you all. Thank you for your attention. Thanks to everybody on the panel. If I could just ask you all to remain seated just for a few minutes.
In exploration, there needs to be the set of people who have no rules, and they are going into the frontier. I've never heard of a moment in history where an entire field is hinging on a single event. The Large Hadron Collider, the biggest machine ever built, is finally going to turn on.
You take two things and you smash them together. You get a lot of stuff out of that collision and you try to understand that stuff.
Could be nothing other than just understanding everything.
Little did I know when I started that the experiments would take 30 years, and here I am still not knowing. I really want to know the truth.
The first time I ever saw it, I can remember walking in and just being stunned, like, 5 stories completely filled with custom designed, hand-soldered microelectronics.
There are 10,000 people, over 100 nationalities. 100,000 computers deal with the data. In fact, the World Wide Web was invented at CERN so that physicists could share the data.
This is really my generation's only shot.
Let's get started, everybody. Now comes the day of reckoning it.
Given the complexity, they're already about a week or 2 behind.
We're saying that all their tools are breaking.
It begs the question, what are the risks?
It would be a catastrophe for physics. These helium leaks are really frustrating.
You've got magnets sheared off their jack. Completely catastrophic.
We're at a fork in the road, and it's cranking up the suspense as much as it possibly can.
We may discover additional space dimension, the mystery and the origin of the universe.
We may be at the end of the road.
The entire control room is like a group of 6-year-olds whose birthday is next week.
It's incredible that it's happened in my lifetime.
Whatever we learn is going to have a dramatic impact on the way human beings think about the universe forever.
So this is a very unique moment. I think it may never happen again, that and hasn't happened, where actually everybody is here at one time. And we have a very interesting distribution here. These are the experimentalists, and these are the theorists. And yes, well, okay, Mike sort of straddled things, actually. But I'm putting him in the experimental side, anyways. But this separation is something that people outside of physics don't really understand that much. That it's a completely different culture. And one of the things that comes out in the film is that they have really different perspectives and different attitudes. And I think that one of the great things about the LHC and the film is possibly that it brought them together in a way that had not been as pronounced before. But I want to just look at a couple of clips from early on where we hear a little bit about the different attitudes that the two camps had towards each other, and then think about how that may have changed. Next clip, first clip.
I always get the impression that theorists think that experimentalists are failed theorists, which is not, I would like to say, what experimentalists think about themselves. But I remember once when I was a grad student, and a fellow grad student of mine, was lamenting about how challenging theoretical physics was, and he says to me, "Oh, I think I'm just going to join experimental physics. It's so much easier." And he says to me, "Oh, what do you guys do? Just bang on a hammer all day? Bang around with a hammer all day?" And I was thinking, God, I don't think I've ever used a hammer in my entire career as an experimental physicist. Is that really what you guys think about us? That, we're just like knock, 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 like some sort of cave people? Every time I go into the theory coffee room, it's like either A, they're drinking coffee, or they're just kind of writing something randomly on the board, or they're like reading magazines. Physics magazines, I'll give them that. So, I mean, you kind of like, it does seem like a life of leisure, actually, in some ways. It's kind of nice.
And on the other hand, some of the theorists actually, because this experiment was going on, they thought maybe I should actually get closer to the experiments and actually try to help them, because they need a little bit of guidance. And so we have Nima's perspective. Roll it.
The experimental community is like a big, huge, multi-headed hydra. There's no one single boss. There's no one who runs the whole show. So it's complicated to know who to talk to, how to make sure things get done, how to even approach broaching the subject of having theorists and experimentalists collaborate more closely. I used to say that for a while in the beginning it was like being in a David Lynch movie. That you would wander around and just keep meeting strange characters, and you had no idea where they fit into the grand scheme of things.
Thank you.
So I'm just curious, what you people have finally met. I mean, do you think that has your perspectives changed at all? Well, Nima just said his hasn't changed at all.
It's still like a David Lynch movie, but it's one of the David Lynch movies that makes a little more sense than the others. So you eventually realize that Fabiola is extremely important, and it's important to be on her good side.
Okay, experimentalist.
Can I say something? Yeah. Okay, so I agree with what Monica said. I subscribe. However, I never used a number in my career, but I'm very good at soldering and welding. Actually, I learned several practical things. No, jokes aside, I think we are very good. We are very good friends. I think that it's very nice that we have the opportunity to discuss very often, and to give them the impression that they give us guidance, which is not true, and to tell them where the truth actually is, because sometimes they're a bit, say, disoriented.
Actually, if I can also make a slightly serious comment, that the issues that I was talking about back then really had specifically to do with ways in which searches for new phenomenon would be carried out, and that's something which in the intervening time, exactly this kind of collaboration between experimentalists and theorists, much closer collaboration than existed in the 10-15 years previous to that, has really made a significant impact on how these things are done. And I really wouldn't make the same comment today. Things are in much smoother and better shape.
Well, Savas, has your attitude towards experimentalists changed?
Actually, I always felt close to them, and I've been talking to them throughout my career. So I don't feel this dichotomy to the same degree that was reflected in these clips. Maybe they were chosen because they were extreme, just for fun. But I think we are much closer. When without them, we wouldn't know the truth. And without us, they wouldn't be able to organize the truth into a structure, a coherent logical structure.
I mean, do you think the LHC represented something different in terms of bringing you closer together? That there was closer collaboration than possibly in past experiments?
Well, I think that one of the things with the LHC is that basically before the LHC turned on, we really didn't have a significant amount of data. And so I think there was sort of naturally then in this waiting period, I mean, the LHC took 20 years to build, and that in this waiting period of these 20 years, there was really nothing for us experimentalists in which to talk to the theorists about, And so now I think in the last couple of years, that has just been revolutionized. We have terabytes of data, and so now we can go and say, well, this is what we found, or this isn't what we found, and what do you guys think? And there's a lot of back and forth now. So I think the data sort of has changed everything.
I mean, Martin and Mike actually both started in theory. I mean, in a sense, you said you originally thought you were interested in theory, and Mike, you got a degree in lattice gauge field, right? So, I mean, you started in theory, you've moved more towards the experimental side, and totally in Martin's case. I mean, did you make the right decision?
Yes, I never regretted this decision. I started in theory. During my studies, I spent a year or so deeply going into theory and quantum field theory and so on. But I think this was just natural, also for a particle physicist afterwards. And well, then the choice actually came because it was really CERN which. This opportunity at CERN to work there and to work on these big experiments, and that happened to be as an experimentalist, and that's why I signed up as an experimentalist. But it's true, I mean, if this would have been possible as a theorist, maybe I would have done a totally different career. But anyway, for me already at that point, it was clear that this is a close collaboration. Yeah? It's clear that one cannot exist without the other. Yeah? So theory without experiments, they would just develop ideas, and they would diverge. And experimentalists without theorists is a bit, you measure, but afterwards you need an interpretation. And you need, and very often the measurement itself can't tell you so much, but of course the interpretation and how it fits into the theory, these can explain you many things. and that's why also the LHC has impact on theories of Big Bang, on dark matter, and so on. This is because there's this interpretation.
If I may add, I mean, having theory developed before the experiments actually happen is also very useful, because that pinpoints the type of signatures that experimentally should look for. So it's very important. For example, the missing energy signature of supersymmetry. I don't think it's something that's obvious before you have some theories that have this as a signature, and many other things. There is a famous saying which says that you have to believe it to see it. You have to know ahead of time what you're looking for to be able to see it.
So just going back to what people thought they were going to see at the beginning of this, I want to just look at a couple of clips from some first interviews of what people up here were thinking before it actually turned on. Next clip.
I think that we are not in a crisis, but we are really in front of a brick wall at the moment. We need absolutely some input from experimental physics, from collisions at high energy to move on.
You know, the worst possibility is they discover the Higgs, nothing else. The new deep physics, dark matter, supersymmetry, extra dimension, it's just around the corner, but the LHC can't quite do it. And there's no way we're going to convince anybody that it may be just around the corner. It's worth building another machine. So the field ends because of that, a miscalculation.
You really begin to doubt whether we can actually make this thing work.
So, before, where are we now, actually? What would you say?
Mine was the most dramatic statement, I guess. I mean, part of the motivation for the movie was that when we were up at night, I remember a conversation with Nima at 3 o'clock in the morning at CERN, thinking, what if we, as in theorists thinking about physics at these energies, we're just on the wrong track, and that what would be revealed would be that this program, at least what we had dedicated our theoretical careers to, or most of them, just happened to be a wrong turn, and we had to go some other direction. And that sort of emotional drama made me think somebody has got to record this. But that sort of drama is a very human drama. It's a generational drama. It's that we people may be affected negatively. That, you know, you could look back and say the career didn't amount to much because you didn't move in the direction that brought us real progress, or at least visible progress. But all those dead ends are incredibly important. Regardless, we need to explore all directions, and it doesn't matter. This is actually something Nima has said in one of the interviews, which it doesn't matter what happens to you. It's not about you. It's not a personal thing. It's necessary for so many people to be pushing in all directions, because we don't really know what the big answer will be, or the next piece of information will be. Now, the LHC has seen the Higgs. I felt much more emotional about that than I expected to feel, because one thing about the distinction between theorist and experimentalist, theorists might read a blog rumor and decide they know what's going on, and experimentalists will wait until the probability that they've seen an accident is 1 in a trillion, and then they'll say publicly that they've discovered something. So that distinction means that we're speculating in many possible futures, and so when you hear me talking a few years ago, you're listening to me, you know, speculating down one path or another. And I know Jerry, who's here, told me that the problem with the theorists is we talk way too long. But I'm going to say one more thing, and then I'll shut up, which is, I think, especially Americans, particle physicists suffer from post-traumatic stress disorder, because in 1993, while building the biggest experiment ever in Texas, a factor of 3 times larger than the one in Geneva, Congress decided to cancel it after spending $2 billion and digging 14 miles of tunnel. And that shook the field in the United States to a degree where we stopped thinking about physics all the time, and we started thinking a little bit sociologically. Like, will they allow us to, can we keep going? Can we push in the direction for pure knowledge and pure science and basic research. There was a mistrust in the people who, up to that point, were supporting this kind of thing. And so that added to the drama, especially before the machine turned on and a beautiful discovery was made.
Can I just add something? So you should know that the Higgs is a crazy particle. And it holds a really enigmatic place in our understanding of the world. On the one hand, it's been, as you all know, it's been anticipated for almost 50 years. So maybe you didn't know, but it's been hypothesized, and people have been expecting something like it for a long time. So from the point of view of a theoretical physicist, it's in the canon of things which is allowed. You know, we understand it very well. And it's the simplest possible solution to a very fundamental problem, which I won't explain now in detail. But anyway, it's the simplest possible solution. On the other hand, it's absolutely shocking that something so simple is actually realized in nature, and I think that's that shock is something which even as theorists, I mean, we've known all of this in principle for a long time, but if you ask, you know, David many years ago when he made that comment, I think it was commonplace amongst theorists to think, well, yeah, we know the Higgs is there. You know, it's about what's sort of coming next. And I think something which has happened to all of us in the interim is, as the actual reality of this damn particle came into existence, and in fact the sort of particular strange mass that it has also became evident, is we're all appreciating much more deeply how utterly bizarre it actually is, that something so simple does describe nature. We've never seen anything like it before, anywhere in physics. There are all kinds of different systems that people can engineer in the laboratory that have qualitative aspects of the physics very much like all the rest of the particles and the forces and interactions that we're familiar with in the vacuum of our universe, but never a Higgs, never something that looks like a Higgs. So that the fact that on the one hand, the simplest possibility is what's realized, but on the other hand, that simplest possibility we've never seen realized anywhere else is absolutely bizarre. And I think we're all appreciating how bizarre it is and taking a step back. What's transpired at the LHC so far is not exactly what some of us expected. On the other hand, it's not so different than what some others of us expected. And we're left in a strange quandary. The idea that experimental high-energy physicists, especially in this country, suffer from the post-traumatic stress disorder of the superconducting supercollider is absolutely correct. And as David said, it colored a lot how we even think about justifying what we want to do. But in fact, the real justification for doing what we're doing is to keep pushing the frontier and seeing what's there. And in particular, since we've never seen anything like the Higgs before, it's very important to study its properties in detail and to go to even higher energies and see what its quantum mechanical properties look like. And while it might be difficult to convince people in this country to do it, Europe is showing some ambition to do something like this, and also China may be showing some ambition to do something like this. Build the next accelerator, you know, 3 times bigger than the LHC even. In 20 or 30 years, this is something people are starting to take seriously.
Experimentalists are chomping at the bit.
Okay, so first of all, following on what David said, you have perhaps picked up another difference between theorists and experimentalists. They work overnight, we work on daytime. So we sleep overnight so that we are lucid on daytime and we can, okay, seriously. So as an experimentalist, first of all, we have just discovered a new particle. It's a very special one. It's completely different from the other elementary particles that we have observed until now. There were 16 elementary particles before the 4th of July. The Higgs boson is the 17th particle, and it's completely different from the other. It's a very special one for reasons that will be a bit difficult to explain, a bit technical reasons. But you know, I consider it the Higgs boson as a new friend. And as a new friend, you want to know him, her, it better. So we have to measure its properties in more details. For that we need more data, and Mike will give us more data, right? Said yes. And so first of all, this is a really very nice thing to do, to measure the Higgs boson in all possible details, because it can be a door to new physics and to better understanding also the universe and many things that we don't understand today. And the second thing is that the LHC just started the exploration of the new energy scale. We've been operating at an energy which is a factor 1.7 lower than the design energy of the accelerator. So in 1 year from now, we will get close to the design energy, and we have been collecting an amount of data which is a factor of 10 less than the design value, and a factor 100 less of what we can do by pushing the machine to its extreme possibility. So we just started, and so it's for me it's like opening the door, and the expectation is still very high to find new physics in 1 year from now. It's like in opening the door and being in front of I don't know, a nice garden with a lot of flowers.
And Mike, I mean, you expressed concern, are we ever going to get this thing to work? You're responsible for delivering beams to these people and worrying about it damaging their detectors. I mean, do you feel unease now? The machine, for everybody who hasn't seen the film, doesn't know, the machine was turned off. They're doing major renovations and upgrades. They will start again at the end of next year at essentially double the energy. And what's your feeling now, Mike? Are you confident now that the next one, it's going to go well, easy?
Yes. Okay, I think
this is for their benefits. Yes.
We were lucky. I mean, the LHC was initially conceived in '84. Took a long time to develop the ideas, develop the magnets, the technology required. It was late. It was over budget. We turned it on and we blew it up, and we were off for over a year picking up the pieces. So we started back up at the end of 2009, and we've just come about halfway through a long shutdown of about 2 years to consolidate the machine so we can take it up to design energy at the beginning of 2015. So I think it's fair to say an awful lot of lessons have been learnt about the process, about what went wrong, about the technology, and those lessons have been applied during this shutdown. So I think the results that are coming through give us some confidence that we can go to the 6.5 TeV without too many problems.
And I'm sure they're all very comfortable to hear that, comforted. So I want to actually look at another side, which is, David said, we really also, I mean, the film really shows the human side of these characters. And they are really, I think you already get a sense, they have more dimensions than just what typically people think of as physicists. And one of the interesting things is that several of our characters play the piano and talk about certain parallels between art and physics. And I want to just show the next clip, actually.
Mit dem Kontrabass saßen auf der Straße und erzählten sich was. Da kam die Polizei und sagt, was ist denn das? 3 Chinesen mit dem Kontrabass.
So, do you think, I mean, what is the role for you in music? And do you think there is an overlap between art and science? Do you think artists can learn from scientists? Do you think scientists can learn from artists?
I want to speak too much, but for me, music is it's a very important component of my life. I think I am a modestly good physicist because I've been studying music, and music and physics are really very close to each other. They both require rules, mathematics. Music is based on harmony, and which is the physics of sounds, essentially. And a Bach cantata, for instance, is a piece of mathematics, because Bach was really following the rules in a very strict way, on top of which Bach has put all of his heart. So music is rules and a lot of creativity and fantasy, as much as physics. So for me, they are really two different expressions of the same human. Do you want to say something?
Well, I was the last child in a family, so my parents were sick and tired of teaching music to their kids by the time I was born. So unfortunately, even though I love music, I don't play an instrument. On the other hand, it seems to me that the creative process has some across the sciences and the arts must have some similarities. One of the things they share is that they appear that they are not very, let's say, they are not very practical endeavors to start with. They don't have an obvious utilitarian value, either the arts or the sciences to start with. Yet they are very important for human beings. And that, for example, is a similarity that comes out at the very end of the movie. That they seem to be not needed from the evolutionary point of view, yet they are there, and it's a mystery for why we do art and science, and why we don't satisfy ourselves from much more mundane activities that are more directly essential for our survival.
You want to say something?
Well, I mean, this is a big subject about which many platitudes are said, the relationship between art and science. But I think there are, at least I don't think it's true for all the arts, but there are certain parts of the arts that are extremely similar. I think. Psychologically, to what we do in physics, very particularly what we do in theoretical physics. I think certain kinds of novelists and composers go through a very similar process we do as theoretical physicists, because there's a structure and there is an external notion of right and wrong. Now, of course, we have an external notion of right and wrong, which is almost literally God-given out there in the universe. But really great music and really great novels also have a sense that there is some perfect structure that you constantly fail to live up to, and you keep chipping away at it until finally some jewel emerges, which was sitting there all along, sort of inevitably there to be discovered, but which takes an enormous amount of time to actually, time and persistence to actually find. So I think that's a fundamental psychological difference that I've talked to Mark about this. I had a conversation with Ian McEwan back in November at the London Science Museum, and we had a wonderful conversation and had a very interesting dinner afterwards. And it's very, very similar. I mean, the basic psychology is very similar. As far as things like playing the piano goes, I don't know how you guys feel about it, but in sort of the opposite direction, and it's a difference between playing and composition. I find that things like playing the piano are a wonderful antidote to the frustrations of research. The hardest part of our job is that you wake up in the morning and you work very, very hard and you have nothing to show for it at the end of the day, and you fail miserably over and over and over again. And we're not idiots. We're trying this, we're trying that, we're trying the other thing, and maybe you take a little bit of solace. You failed a little less badly today than you did yesterday, but it's but mostly you fail, and every now and then. If you're Savas, it happens more often than for some of the rest of us. You have a big peak, and you're maybe excited for 2 or 3 days, and that's it. And then you're back to the misery. Okay, so that's life, and that's what you have to get used to if you want to be in this business. When Monica was complaining about us, drinking espresso and just chilling all the time, it's hiding the suffering underneath. But playing the piano, by contrast, is something that what you practice, you get better, and it feels good. It feels good because it's not true for anything else we do. So.
Actually, that may be a nice lead into, don't do the very next clip, but the clip after. Yep.
Coffee is a very serious business in the life of a theorist. It's not like physics research where you can wait for 30 years before you know if you are right. Within a few minutes, it pays off. If you succeed, it's great. If you fail, you get to try another one in another minute. In particle physics, you construct a theory 20 years ago, and it may take that long before you know if you're on the right track. Jumping from failure to failure with undiminished enthusiasm is the big secret to success.
So I think that really is sort of a key in many ways to continuing this. And the life of a physicist, though, is a very particular mode in either case. And I think before we open it to questions, I just want to end with now go back to the penultimate clip in terms of Monica.
I have a friend who works for Google, and when he says he's on a plane and he works for Google, everyone's like, wow, that's awesome, you work for Google? And I'm on a plane, and I say, oh, I'm a physicist, and people are like, yeah. Where's my reading material? And, but the thing is that I essentially do, on a day-to-day basis, the same thing that people do at Google. I mean, I write huge optimization algorithms, I write programs, I mean, actually, many physicists, when they leave physics, go to Google. And yet, on one hand, people are like, Google, cool. On the other hand, physicists, you're just like, geek.
So, I hope you get a different appreciation for people here. But I think at this point, I guess we will open it up to any questions that anybody may have.
And come up to the mics. There's mic here, mic there.
Hi, thanks for coming in today. I had a comment on the sociological issue that you mentioned before. I would say that I'm of the minority in that I would appreciate tax dollars being spent on the pursuit of pure knowledge, and I would read up on what you find, and I would be in that part of society, but the majority would probably want to see what's the practical benefit of that's going to come out of all of this. So I wanted to ask you all, what are your thoughts on that? What if we were going to call our congressman and ask for more dollars to be spent on your research, what should we say?
Can I say something about that? So just so you have an idea of the scale of the projects that we're talking about, when we say a big accelerators cost $10 billion, that's 1 part in 10,000 of our GDP. Over 20 years. So this is it's a lot on the scale of scientific projects, but it's not it's not backbreaking by any stretch of the imagination. Now, normally when this kind of discussion comes up, we talk very appropriately about the completely unanticipated consequences of curiosity-driven basic research. People go back. Faraday, when he was famously doing his experiments on electromagnetism, some minister came to see him and asked exactly your question. What is this good for? And he famously responded, "I don't know, sir. I don't know, sir. But someday you will tax it." And that was correct. And it was 20, 30 years before people knew about radio waves and our entire technological life is driven by that. People in the 1930s were doing experiments to try to understand, detailed properties of the hydrogen atom and strange mysteries about how atoms can even work that led to the development of quantum mechanics. Now, quantum mechanics in the year 1927 was perhaps the most esoteric branch of science, and relatively speaking, the most esoteric branch probably we've ever seen. There were maybe 6 people on the planet who understood it. And yet, no one could have foreseen that 30 years after that, our detailed understanding of the quantum properties of matter would lead to revolutions like the transistor. And again, by some measures, 2/3 of our GDP is directly a consequence of quantum mechanics. So people talk about that. It's very appropriate to talk about that, and that's the most fundamental reason to do this. We push boundaries, and particularly technological boundaries, and in the process of doing that, inevitably, you have to bring so many people together to solve such difficult problems, especially technical problems, that great things are bound to come from it. Again, famously, the World Wide Web was developed at CERN again originally as a method to allow physicists to share information efficiently. And something about scientists is that we don't care about money. I mean, it's maybe strange, but we really don't care about money. Anything we discover is just as part of our culture, is something for the world. So all those things are true. But even, if you want to be a super hard-nosed, pragmatic, practical guy and say, but come on, an actual, quantifiable dollars and cents, what do I actually get from investing in literally your accelerator? Well, there was an interesting study that was done, not a study, but a sort of a half study, but I think fairly plausible, that was done about the impact of the big accelerator we have in the U.S. Outside Chicago, that was ultimately shut down. That's the sad end of U.S. high energy physics. At least our leadership in this particular frontier. That accelerator costs around $5 billion over its lifetime, and if you actually look at concretely the number of highly trained sort of PhDs, for example, that were trained by this. The U.S. Census Bureau gives a dollar figure to how much a PhD is worth. It's worth $2 million. Okay, as far as so just the number of PhDs that were trained already made up for the $5 billion spent, and then on top of that, the infrastructure that was there for developing magnet technology, for developing things that ended up being useful for cloud computing and so on. If you're even very conservative about how, and those industries would have succeeded anyway, but even if you're very conservative about just even a mild speed up to the development of those industries, you're talking about $50 billion. It's a 10-to-1 return on investment easily. So by any measure, it's 1 part in 10,000 of GDP. It's a 400-year tradition of pushing the technical boundaries of the world and giving a template for how you go about solving seemingly impossible problems, and even very directly with the technologies involved, a large return on investment. I think it's a no-brainer. But given that the scale of money is large, that this argument needs to be made. It needs to be made clearly.
And everybody on this panel will be happy to elaborate on it even further. Next question. Let's.
Over here, Mark.
Oh, Jerry.
A couple questions, if I may. Well, first of all, was Enrico Fermi unique as a highly accomplished theorist as well as experimentalist? And if so, why don't we have more such today? And when theorists hang out and talk shop together, are they talking concepts, or are they talking math in a semi-pure sense, or are they just, I don't know, bullshitting brainstorming?
Well, let's let the experimentalists talk about Fermi.
So I'm a huge admirer of Enrico Fermi. He was a great physicist, and he was a great experimentalist and a great theorist.
Let me just say, Monica had an Enrico Fermi scholarship, actually.
Fellowship, yeah, exactly. So
I had the privilege of visiting a friend there about 35 years ago.
Okay. So, and I think the times have changed a little. I mean, in Enrico Fermi's time, he could do an experiment on the time scale of a few months to a year. And the difference between the LHC is that in order to reach these energies that we need to reach, that we're talking about building an accelerator, starting an accelerator in 1984 and having it turn on in 2009. And so this is kind of, in that way, forced specialization into kind of the experimental side versus the theory side. But I think that this has really been changing a lot now that we do have data, and we will have data now for the next couple of years. I mean, as the machine will continue to deliver and more data, that we can then, I think it will go back more towards the sense that experimentalists and theorists will be talking with each other and figuring out what we should look for next, what we found or haven't found fits into theories and so forth. So I think it's working more towards how it was in Enrico Fermi's time, but I think there was a phrase we always use in my group, which is that if it was easy, it would have been done already. And so essentially all the things that you could have done in 2 months has essentially been done, and now you've got to do everything in 20 years.
Okay, Savas, what do you
So as far as what we talk about, well, we talk about all of the things that you mentioned, but most of the time we talk concepts and equations and pictures. We mostly think, at least from my circle of friends and myself, in terms of pictures when it comes to solving specific problems. Most of us rarely think at the level of equations, which is what the public seems to think about, as it's mostly in terms of pictures and concepts. And the equations come near the end to justify the pictures. And often they justify, sometimes they contradict the picture. But it's the final test.
If I may, just a punchline of a joke that I like that no one else does, but I bet you guys will. And I'll just do the punchline. So a string theorist is explaining to his artist friend how he understands things. And he said, oh, I just visualize it. And the artist says, how do you visualize 11-dimensional space? He says, simple. First, I visualize n-dimensional space, and then I let n be equal to 11.
So the Higgs boson was postulated in the early mid 60s, and it took us until a couple of years ago to actually track it down. So why was that? I can kind of think of a bunch of reasons, like money, like theory, like building magnets, that the computation, and you're not allowed to say all of the above. What were the sort of the long poles and the constraints and sort of getting from there to here?
Well, oh, sorry.
Yeah, well, I think, I mean, the main reason was that the Higgs has its mass, which it has. And that was not known, by the way, when it was postulated. One would have thought that the next generation of accelerators might see the Higgs already. I mean, there are papers where it's even below a GeV and so on. Turns out to be 125 GeV. And, well, so it was clear that such a heavy Higgs boson needs a big machine which can actually create it. And we were a bit, if you want, unlucky because the lab was just on the edge. The previous accelerator at CERN actually was just on the edge. Also, Tevatron was just a little bit too little, and then LHC got it. So,
but we've known something is going on at roughly these energy scales or distance scales, depending on how you count, since 1895. In 1895, people discovered radioactivity. And if you think about it, this is a completely insane thing. You have a nucleus that's sitting there, or let's make it simple. You have a neutron. You take a neutron in empty space. It sits there for 15 minutes, and then it disintegrates into a proton, an electron, and something called an anti-electron neutrino. But anyway, 15 minutes is a gargantuan, long time scale compared to all the time and distance scales of atomic and nuclear physics. And we now understand why it takes so long. It's because that the physics that's ultimately responsible for making the neutron disintegrate operates at distances that are in turn 100 times smaller than the nucleus itself. And so people indirectly knew about the scale in the 50s, as I said, even in 1895, but we properly understood the way to conceptualize it already by the 50s and 60s. And it wasn't until the 1980s that we actually discovered the particles responsible directly for radioactivity. And then the fact that it's another 20, 25 years after that before we go another factor of 1.5 higher in energy. Had the Higgs been down there, just a factor of 2 lighter than it was, it would have been discovered in the 1980s. But this is a difficult business, and so every time you need the sort of next generation machine to just push the energy frontier a little bit, you're talking about another 20 years investment. So so it actually makes perfect sense that it took so long.
I want to argue that you shouldn't stop at Particle Fever 1. Where's Particle Fever 2? The story is not over. Dark matter is not discovered. And there's a continuation of the human story as well. The whole conversation about the accreditation of Higgs, the dual award of the Nobel Prize. More movies like this is good. So
well, that's very good to hear. And just a very commercial plug. The film opens today at the Film Forum, and so you can express your enthusiasm for the film and for future films. It's playing at the Film Forum this weekend, or well, for a couple of weeks. It's opening in LA. It's opening across the country, and obviously, I mean, the great thing is. I think the greatest thing is that people come out of the film and they do want to know. And I hope people will follow it. Whether it turns out to be a film and has all the drama that this one had is going to depend a lot on these people sitting to my left and what they find. But we will certainly be keeping people updated, and I hope people come out of the film, they want to know, I mean, that's what everybody, after many of our screenings, one of the first questions is, have they found anything else? Are they going to find something else? When are they going to find something else? And when's the sequel? And all of those are very interrelated, and we will see. And I think we're all extremely pleased to have just tapped into an audience that really does want to know, and hopefully we'll be able to provide the answers when the machine turns on again.
My name is Jeff. I'm a fashion designer and a creative director, so I couldn't be more layman than anyone else in this room probably, but I'm very interested in what you guys are doing. You mentioned that the current LHE is under construction and is being renovated for double the power in a couple of years. Can you explain when that opens, at best case scenarios, if all your dream scenarios came true, when that thing reopened, what does that mean? Like, what could you compare it to in world history? Is it like discovering the wheel, or is it time travel, or is it the World Wide Web, or like what can you compare it to that has happened in history that this will be the outcome?
Oh. No, go ahead first. Okay, so since I'm a professional dreamer, I'll tell you my best case scenario.
Best case scenario
is we discover new dimensions of space. That instead of 3 dimensions, maybe there is 10 extra dimensions, 10 total dimensions, let's say, of space and time. And that we find that these dimensions are relatively large. By large, I mean a little smaller than a millimeter, which is really really big from the point of view of the atomic nucleus. And this corresponds to finding, inside this new dimensions, there could be parallel universes similar to ours, or maybe with different laws of nature. Maybe there are parallel universes where the electron mass is different than what it is in our universe. And somehow this can give us access. Finding these extra dimensions creates the space inside which you can have new worlds.
When is the last time we discovered a new dimension?
Well, in a sense, time has been adopted. The most fruitful way to think of time, it turns out, is in a way that's democratic with space and time, that there is some close interconnection. And that was in the early part of last century, the early part of the 20th century, this realization was made. And it, in fact, stemmed from Einstein's theory of special relativity. That's the best way to understand the theory. So that is the last time. What I would draw a parallel with is perhaps the discovery of new continents, but this is a very vague parallel. It's really new worlds. You can fit many, many parallel worlds with even different physical properties. And some particles, like what we call the graviton, the particle that is the cause of gravity, can travel inside these extra dimensions and somehow access these worlds. This is a theory that in fact exists. It's a theory that Nima Arkani-Hamed and I. So there is mathematics behind this. It's not just discussion.
Oh,
And
it
in
could
fact,
be science fiction. It's
it
just,
could be.
it's rigorous, that's all.
It's
science fiction.
There is math. So somewhere in the Platonic world of mathematics, this structure exists. Whether it is realized in nature or not, that's what people on the left will decide, hopefully soon. And so that is probably the wildest dream. And in fact, to underline that it is science, there have been tremendous experimental constraints that have already been set from the first run of the LHC on the size of these dimensions. So it's that is the wildest thing. There are somewhat more spectacular discoveries that involve a theory that's called supersymmetry. That is a bit harder to visualize, but you can perhaps think of it as a new dimension that has weird properties. So that would be, my number two scenario. But I'm sure other theoretical friends have.
Well, I think we should let the experimentalists speak.
Well, going back to the initial theme of this discussion, difference between theorists and experimentalists, you also realize that theorists talk a lot, and they are not shy at all, and we are much more quiet and more shy. No. No, seriously, I think what Savas said is very nice, very good. And for me, already the discovery of the Higgs boson was something quite special and really revolutionary. And I like to compare it to the man on the moon, not only because of a big jump in some sense in the kind of big jump in our accomplishment of mankind, but also because of all the technology that is behind. The man on the moon is not just going there and putting a flag on the moon. Is all the technologies that has required, that has been developed to achieve this step. And going back to the discussion about why we are spending so much money in fundamental knowledge, of course, there is an important aspect that in order to to make step forward in fundamental knowledge, in some cases you need a lot of technology, and this, of course, so you need technology to advance fundamental knowledge, and fundamental knowledge in turn allows you to improve your technology. So it's kind of a virtual and positive, it's kind of a virtuous and nice loop between knowledge and science.
Did we ever get that last clip converted? Excuse me? No? Okay. So you want to wrap it up?
Yeah, we should probably wrap up, but thank you so much for coming. This was just absolutely fascinating, and we're thrilled that you came along. All the best for the premiere tonight, and thank you.
Thank you.